Hi everyone, I'm Yukang from Tsinghua University. Today I'm very happy to share with you this paper, HeadCross, Exploring Head-Based Crossing Selection on Head-Mounted Displays. This is done in collaboration with Yingtian, Chun, and Yuanchun. First, let's take a look at what is a HeadCross and how it can benefit users.
We take the document reading as an example scenario. The user reads the document on AR headset and take notes on the paper. Currently, using hand gesture, users need to frequently switch from performing hand gesture and writing with a pen. With HeadCross, users can cross the scroll bar. They can write notes with hands and scroll the document with head movements.
As the video shows, it enables hand-free interaction with user interfaces. It provides a supplementary input method other than hand input, and it can be helpful when our hands are occupied by physical objects or by other tasks, or simply when we are lazy to raise the hand to the midair. With HeadCross, users move the cursor by head movements. To select a target, the users move the cursor across the target boundary and cross back. To recognize this cross behavior, we basically detect a sharp turn inside the target and the close distance between the entrance point and the exit point on the target boundary. And similar to recognizing other kinds of gestures, we also extract the features on movement trajectory and speed changes. We conduct user study 1 to observe and understand the user behavior patterns when they perform hand cross in comparison to pass and dwell on the targets. We also tested how the target size and the target density influence the head cross behaviors. This video shows the test conditions. For the factor target density, we only tested 2 extreme cases, showing a crowded layout or only show 1 target at a time. Through this user study, we find head cross behavior has the difference on movement speed and entry direction compared to pass and dwell action. The figure above shows the distribution of the direction in which the cursor entered the target boundary. The entry direction of head cross actions mostly are from 4 main directions. We also analyzed the influence of target size and density. Target size significantly influences the movement speed, pass length inside the target of the head cross actions, and the target density significantly influences the distance from where the user starts to perform the head cross actions. Then we conduct user study 2 to evaluate the performance of head cross. We selected 2 common target acquisition tasks, text entry and menu selection. Text entry is to select the characters on the keyboard to form the target sentences. Menu selection is to select the options of the menus. We tested 1-step and 2-step menu selections. We compared HeadCross to devolving-based selection, hand gesture method, and the selection with VR controllers. The test conditions and the procedures are shown in this video. The results show that HeadCross provides similar performance to devolving-based selection method, and it outperformed hand gesture method in speed, accuracy, and the perceived fatigue. And in VR, selection with controllers results in the shortest task completion time. As HeadCross is only one of the instances of head-based selection methods, we also compared other designs of selection confirmation. We compared HeadCross to point and nod, which does not request a double cross on the boundary. Point, dwell, and nod, which include another dwell to avoid false positives, and inside, outside, inside, which requires a triple cross. As the results showed, point and nod is not practical, because of the high false positive rates and the resulting wrong selections. The other three designs provide similar performance. For user preference, pointed out is also outperformed by the other three designs. This figure shows the selection patterns of the 4 designs. To avoid false positives, pointed out forces users to go around the keyboard while typing. As a summary and discussion, we provide head-based target selection method, but we are not trying to replace hand input, but we want to supplement it, especially when our hands are occupied by other tasks. To be mentioned, we implemented HeadCross on AR and VR headsets, but actually it can be applied to many other kinds of platforms. For example, if applied to smartphones, we can use the front camera with computer vision algorithm to locate the head position and estimate head orientation. With one hand holding the phone, HeadCross will support one-handed interaction. As you can also imagine, HeadCross can also support mouse-free interaction with the desktop computers. So that's all.